I'm Nicole Lunning. I'm a postdoctoral fellow in the Department of Mineral Sciences, specifically a Peter Buck and Smithsonian Institution fellow. And my talk today is on making pocket-sized planetesimals, petrological experiments on meteorite samples. I want to start with a little bit of background on meteorites. Most meteorites come from our solar system's asteroid belt, which is located between Mars and Jupiter, and they're knocked off of their asteroids, and if then these pieces knocked off of asteroids become Earth-crossing, they can fall to Earth as meteors, and if they make it to the surface, they become meteorites, many of which we have in our collection. So what are asteroids made out of? We have pieces of meteorites to look at them, and we know from this that they are some of the oldest things in our solar system, that they come from bodies that formed before Earth and the other terrestrial planets. And these primitive materials include things like solar nebula sediments, if you will. These are things that precipitated directly out of the nebula, as well as things that went through iterations of melting and remelting and processing as material in the solar nebula. So these were the first geologic samples in our solar system. And then all of these solar nebula sediments accreted to form slightly larger but still relatively small bodies called planetesimals. And the first of these to accrete, their source material still contained short-lived potent radioactive nuclides, most notably one that I'll mention later in the talk, aluminum-26, and these provided a heat source for the earliest accreted or coalesced planetesimals, which drove melting on them and what we call planetary differentiation, the separation of a core from the silicate mantle and crust. Whereas bodies that accreted a little bit later, after most of the short-lived radioactive nuclides had mostly decayed, are the best archives of the solar nebula sedimentary material, and they also provide a good analog for the starting material of the earlier planetesimals that differentiated. And in the experiments I'm going to talk to you about today, I'm actually going to melt samples of the later formed bodies, the bodies that still have these primitive solar nebula sediments, to then replicate the differentiation process. And this allows us to look at the separation of the core material from the rocky material, which is a fundamental geologic process in these earliest planetesimals and subsequently later in the formation of the Earth and the other terrestrial planets. And this is a question that's of interest to people like me, meteoriticists, cosmochemists, but also to astronomers who study the formation of solar systems elsewhere in our universe, and to people who are interested in parts of the Earth that you can't directly easily look at, such as the deep Earth, that knowing the starting composition of the Earth is important for, because these are likely the bodies that went into forming the Earth. Which gets into my specific slice of this question, which is in the experiments I'm going to present today, we're looking at how differentiation proceeds on bodies in which iron metal is not stable, which is usually the core forming material in bodies, including Earth. But we have some crustal basaltic samples that indicate they came from bodies where metal wasn't stable, and so they likely had cores of different compositions. So how does differentiation proceed on these types of bodies? And so what I did is I melted relatively small, as you can see from this picture, samples of meteorite material in a high-temperature furnace in the Department of Mineral Sciences. And this is a picture of part of one of my experimental charges. It's a backscatter electron image taken on the scanning electron microscope in this museum. And in backscatter electron images, the grayscale is related to mean atomic number, which roughly translates to density. So the whitest light-colored things in this image are the most dense, ballpark-wise at least, and then the darker are less dense. And so you can see here the white is the iron-nickel sulfide liquid, so on these bodies they would have a much more sulfur-rich core. We also have lots of olivine crystals, which would correspond to the mantles of these bodies, and olivine is also an important mineral in Earth's upper mantle. We have what is quenched liquid and becomes glass once we quench it, which corresponds to the basaltic, that outer crust of these planetesimals, and is broadly similar in composition to the type of rocks currently forming in Iceland and Hawaii right now. And then we had a mineral that was kind of a surprise, this mineral called Hersenite, which is an aluminum-rich oxide. And this led us to consider where the Hersenite would end up in differentiation of bodies like this. And the Hersenite is more dense than both the basaltic liquid and the olivine, so it would likely end up in the lower mantle of these bodies or outer cores. And getting back to that short-lived potent radioactive nuclide, aluminum-26, the minerals that host and carry the aluminum are going to control the distribution of heat in these differentiating planetesimals. So having the aluminum in a denser phase actually will change the thermal structure of this type of planetesimal rather than the ones that we're more familiar with that are more like mini-Earths with a more iron-dominated core and a less sulfur-rich core. Thank you for your thoughtful attention. Actually, for me, I became interested in meteorites at this museum. I was already a geologist, but meteorites are such rare rocks, most geologists don't see them a lot, and I really fell in love with meteorites here.
Has Hersenite been found in any natural meteorites?
It has, but not the ones I'm melting, actually. So the ones that it's been found in are CO and CK chondrites, which have different oxidation states. And it's been found mostly as a metamorphic miscibility phase from magnetite, so rather than a magmatic crystalline phase, crystallizing from a melt phase as we see in the experiments.
As you were doing, those are really small samples, which I assume is because there's not lots of meteorite material around. If you had done significantly larger melting experiments, do you think you would have gotten the same results?
So we did two different types of things that we melted. So what I showed you is actually a pressed pellet of powder, and it's a powder that was homogenized from a much larger sample. It's actually a standard, so its composition is very well known. And then we did do some on chips because we wanted to see some textural effects of the natural samples. And so those are more the ones where you may have some heterogeneity in the sample, but the ones where we're doing pressed powders, since we have a very representative composition, it's a reasonable inference that a larger sample would just scale it up, but we'd see this. Thank you.